자, 안녕하십니까. 우리 지난 시간에 배운 내용, 마지막에서 이제 배운 내용부터 다시 복습을 하겠습니다. 우선에 우리가 배운 내용이 바로 뭐냐면 이제 미분에 대해서 배웠거든요. 그래서 이제 let, 그래서 뭐 f를 오메가에서 이제 복수 평면으로 가는 하나의 이제 함수가 있다 합시다. 하나의 펑션. 자, function defined function and z0 is in omega and suppose that 영어 수업이라서 오늘은 내가 천천히 쓰면서 영어로 이제 강의를 하겠습니다. 지난 시간에는 영어 수업이 늦어버려서 안 했는데 suppose that there exists a epsilon, positive epsilon, such that b epsilon z0 is in omega. So which means suppose we have this is omega and I have z0 here and there is epsilon ball. This radius is epsilon and this is b del epsilon z0 is in omega. Okay. Once you have this, then we can consider the limit. So if the limit h goes to 0 and f z0 plus h minus f of z0 divided by h. So this is the same as limit z approaches z0 and this is f of z minus f z0 z minus z0. So the limit is this limit exists. Then we say that last time I defined differentiable, right? We say that the function f is differentiable at z0, okay, at z0, and we defined f prime z is the limit. So it's the limit, this definition. So limit z approaches z0, fz divided by fz0 minus z minus z0, so divided by this one. Okay, and this guy is called so the derivative of f at z0. Okay, so this is the last time we did at the last lecture. So differentiable f differentiable z0 and the derivative to be defined in this way. Okay. Okay, so this is what we learned last time. And one remark. Let me see. So do we have another definition? Okay, so it is one remark. It's a very important remark. You know, when we define the differentiability of f at z0, we did not assume that the function f is continuous. So remember, we don't have any continuity assumption for f. So which means if f is differentiable at z0, then f would be continuous. Okay, so f is continuous at z0. It's the same as you learn in the calculus. In calculus, if f is differentiable, that f is continuous comes directly. Okay, so it's not difficult to prove, but let me mention that. So when you took the calculus, so you might prove this fact, but you may forget how to prove. So I will give you proof here. Okay, so proof is following. So proof is not difficult. So our claim, so when you want to prove this f is continuous at z0, so you need to prove the following one. So limit z approaches z0, so fz has to be fz0. So that is the goal we need to track. Okay, so let me look at this one. We know that since f is differentiable at z0, so we have what? The limit z approaches z0 and z minus z0 here, fz minus fz0. So this guy exists, right? This guy exists. This one is f prime z0. So this guy exists. So that is our assumption here. So the key to prove this theorem is you have to derive the claim from this one. Okay, from this one. Okay, from here, how I derive this one? It is easy. So it is clear that first you need to use this one. It is clear that the limit z approaches z0 and z minus z0 becomes 0, right? This is obvious, very important, easy thing. And then using these two property, so I'm using this effect, this one, and that one. So this is my equation 1, this is my equation 2. So from 1 and 2, so from 1 and 2, so we have what? We have that the limit f of z minus fz0 divided by z minus z0, this guy multiplied with the z minus z0, and they take a limit z approaches to z0. So that would be one of the property we studied for limit. So limit an exists, limit bn exists. Then the multiplication would be this one is that is f prime z0 times 0. So that we use property 9. So that is property 9 in equation in page 49. So we use that property, so that becomes 0. And C, let me look at here. So Z approach 0 means Z is non-zero, so this would be cancels out. So you can cancel them out. So that give us that limit Z approaches Z0 and then Fz minus Fz0, that is equals to 0. That's what we have. And the final step. So then final step, we need to show this one, the limit, in order to show our claim. So this is f of z. And that guy is limit z approaches z0 and then fz minus fz0 plus fz0. Okay, so from here you cannot directly from this one to our claim. You need one more step. That's what I'm doing here. So then you see the limit this one exists. The limit is constant. So again, by property 8 in page 49, what we have, limit z approaches z0, you can separate into pieces, fz0 because they exist, and then the limit z approaches to z0, fz0. So we know that this is 0, this one is fz0. So finally we have fz0. So that is our claim. Okay. Yeah. I think you, even the function f is a real valued function, you can, this process is exactly the same. So this is exactly the same proof. Okay. So that is what we had. Okay. So what would it be next? So next we go some examples. Okay. Examples. So number 1. So what is the simplest function you can consider? So the simplest function is constant function, right? The simplest function would be constant. Okay. So then f of z equal constant c. This is c is constant. So in this case, for every z, 0 is in complex. So f prime z0 is constant 0. So that is because what? The limit z approaches z0, here z minus z0, and then constant. So fz0 minus fz0. So this constant means this guy is 0, this is 0. So finally this is 0. It's very easy. Okay, easiest example. Second example. Let me look at this function. F of z equals z conjugate. So that means you take z, here conjugate is this one. Z conjugate. Okay. So this is reflection about around z equal real axis, about reflection about, so real axis. Okay, this is the real axis. So this is the imaginary axis. Okay, the deflection function. So whether the deflection function is differentiable or not. So let us check. So you can look at that one. Okay, let's suppose I take Z0 is in complex. So I want to check whether Z0 f is differentiable at Z0. So then so let me consider this one. Limit h goes to 0, h complex number h is f of z 0 plus h f of z0. So this is if the limit exists, then f is differentiable, right? So then this one equals to limit h goes to 0 here h this is z0 plus h conjugate minus z0 conjugate, okay, by definition. And then the property of a conjugate, you can split into two pieces. So that would be h z0 conjugate and h conjugate minus z0 conjugate. So these two cancels out. So what we have? So then we have a limit h goes to 0 here h and h conjugate. Okay, so that we have. Okay, here now this is complex number h. So here let's say h equals s plus it. So s and t are real. Okay, you can write down that way. So then I replace this one by s and t. So h equals to 0 means what? The limit s and t goes to 0, 0, h equals s plus it here s minus it. So that's what we have, right? This is our limit. Okay, so here, this complex plane here, I have here h is in here, h is s plus it, and that one it converts to 0. So you can, first I take one path. So let's take h in here. So case 1, if h equals s, okay, s is in R. You follow here, so you follow this one. Then in this case, the limit h goes to 0, h over h conjugate. In that case, both real. So that means you take h equals s. Then this s goes to 0. S over s equals to 1, right? You take one path, h follows this route, then you have this limit. And in other words, if h follows complex it, okay, so that means you follow this path. So h is in here, converges to 0. So in that case, once you compute the limit, h goes to 0, h conjugate, that would be limit t goes to 0, HITIH minus IH, right? Conjugate. So that, oops, not HIT, IT, so it would be minus 1. So when you take a different path, it takes different values. That implies this f is not differentiable, so that the limit does not exist. So which means hence the limit. So the limit, not limit, the limit, limit z, so h goes to 0, h goes to 0, so it's here h f z0 plus h minus f z0, the limit does not exist. So exist. So this implies fz equals z conjugate. The conjugate is not differentiable at any point. So it's not differentiable at any point z0 is in complex plane. Okay, so this is one of the example which is not differentiable. Okay, and let me look at now different example. Okay, so example 3. What kind of example we have? So let me, our textbook, so look at the z square. Let me look at z square, whether it's differentiable or not. Well, so let z0 is a complex number. So like x0 plus iy0 is in complex plane. So here x0, y0 are real. Okay. Then we consider the limit. So the limit we need to compute, right? So by the way, we need to compute this one. So z minus z0 fz minus fz0. So we need to compute this guy. Yeah, we need to compute this guy. Well, you expect that the derivative is 2g, right? That's what we want to show. So h goes to 0. Here h f z0 plus h minus f z0. So if the limit, let me remove the limit. Okay. Yeah. So let's plug in here h z0 plus h squared minus z0 squared. Well, if this one is 2 z0, this is too easy one. So let me change this function. So z0 modulus. Let me, otherwise too easy. So I want this one. So let's look at modulus one. So the modulus is z0 plus h modulus squared, z0 modulus squared. So the modulus squared is property z0 plus h multiplied with z0 conjugate plus h conjugate, and then g0 conjugate, right? So then you expand these out. So here's h, and gg conjugate is gone, cancels with this one, and then I have hg0 conjugate. I have z0 h conjugate plus h conjugate. So that's what we have. Okay. So case one. Let's look at the case one. So if z0 equals 0, then the limit h goes to 0, h here h, and then f z0, so z0 equals 0, so this h minus f0, then the limit h goes to 0, h is here, so this is 0 0, then you have h conjugate. That's what I have. So then h is cancels out, so that would be 0. Okay, when h goes to 0, h conjugate goes to 0, so that implies f prime 0 to be 0 exists. Okay, so simplest one. So that implies f is differentiable at 0. Okay, so the f is differentiable at 0. How about f is non-zero case? So let's look at the f is non-zero case. So what do we have? So case 2, suppose that fc0 is non-zero. Okay. So in that case, the limit, let's look at the limit. We want to compute this one, h over f z0 plus h minus f z0. So we end up either getting limit h goes to 0. So here, this one. So that is h z0 conjugate. So z0 h conjugate. h conjugate. So that's what. Okay. So here again, so let's take h to be it. Okay, so t is real. Okay, that means we approach h goes this way. Follow here. So the y-axis in the imaginary axis. So in that case, limit h goes to 0, h over h, that h is z0, h conjugate, h conjugate. So let's plug in. So then the limit h goes to 0 means t goes to 0. So h instead of h, it. So here it x0 minus I y0. And then x0 plus I y0. And then h conjugate minus it. And then h conjugate, this minus it minus it. So plus t squared. So h plus t squared plus t squared, right? Then what do I have? So then the limit, so here it, they cancels out. You know, this comma, this one over gone, this is also gone. So when t goes to 0, so what will we have? So t goes 0, here you have x0 minus iy0, and then minus x0 plus iy0, and then the other one equals 0. So am I right? it let me check whether I have a mistake or not. G0. Let me check. H equals to 0. IH. Minus C0. Do I have any mistake? G0, H0. I don't think I have a mistake. So that is the Z0 conjugate minus Z0. Okay. This is what I have, what we have. Okay, what is this one? So then you cancel this out. So that would be minus 2i y0. So that's what I have. So if, let me, do I have another case? Second case. So this is one first case. So let's look at the h equals s. Okay, so s is real. That case, we also compute the limit. H goes to 0, and then h is 0 conjugate z0 h conjugate plus h conjugate. So that is replace h by s. So s approaches 0. Here s z0 conjugate z0 s plus ss. So that implies we have z0 conjugate plus z0. So that's what we have. So z0 conjugate z0 is what? This is a 2x0, right? That implies 2x0. Okay. So here you know that y0 equals real. Here it's also x0 equals real. Okay. So that implies if f prime z0 exists. If this one exists, so z0 is non-zero case. If this exists, then the limit has to be the same. So f prime z0 has to be 2x0 equals to minus 2i y0. Okay. And these are all real. These are all real. So only case we have x0 should be 0, y0 should be 0. So that implies z 0 equals 0. So that's contradiction, right? So therefore, so here are our conclusion. So therefore, the contradiction. Therefore, fz equals modulus of z square is differentiable only at z equals 0. So if z is non-zero, so the function this function is not differentiable. Okay. So we have a couple of examples. One example, simplistic example, constant function, derivative equals 0. Reflection function, so f is differentiable only not differentiable at any point. Okay. Yeah, at any point, not differentiable. And then fg equals g modulus conjugate. This function is differentiable only at z0. Okay, so that's the one. Okay, next I will give you just the rule of derivatives. This is already you are very learning also the same the calculus courses. So I'm now going to prove next theorems. Property, somehow it's property. Okay, before doing this, I will give it just notations. Okay, here I have some notation. So if f is differentiable, at z0, at z, for every z is in some function omega, then we denote ddg f of z. So this one we consider f prime z. Okay, so this is our notation. So here's a property. So I'm not going to prove all the properties. So here, properties. And suppose that f and g are differentiable. F and g are differentiable. At z0. So at z0. For every point. So differentiable in omega. So in omega. Then the first f plus minus g is also differentiable. So it's differentiable. Just use definitions. So differentiable in omega, and then f plus minus g derivative equals to f prime z plus minus g prime z. Okay. Also, cf is differentiable. Any constant, c is any constant, complex constant, differentiable in z, and the cf prime z equals c times f prime z. Okay, this is the first property. And second property, fz g times g also differentiable. So this function is also differentiable. omega, and then f of z, gg prime. So this one is prime equals you have product rule, f of z times prime gg, fg, g prime. So the same as the calculus. And then number 3. So if g z0 is non-zero, in that case, then g of f is differentiable at z0, and then the derivative of this guy prime z0. So you learn in calculus the same formula, g z0 squared f prime z0 g z0 minus f z0 g prime z0. Okay, this is number 3. Also, we also have the composition function. So f is a function from omega to complex, and g is also function from u to complex plane, and also f of omega is contained in u. Okay, so f and g are differentiable. Are differentiable in, oops, let me remove this one. I have to rewrite. So in omega and u, okay, respectively. And f omega is a subset of u. Okay. So then what? Then you can also conclude that the composition function g composition f is omega to complex. So this is differentiable in omega. Okay, omega, and also you differentiate. So this prime g would be g prime fg. We have chain rule f prime g. So we have this formula. The formula is just proof of this formula. The follow is the exact the same as in calculus. Okay. So that would be we finished the page, almost page. I'm not going to prove this one. So although you can find the proof in the textbook, that would be page, we finished the page up to page 60, okay? So you can, let's see, some exercise problems. Oh yeah, so exercise, you should do exercise problem, homework. So homework. Study the number page 62, problem number 9. So you should study this one, okay? Number 9, page 61. Number 8, so you should study these problems. I'm going to put this problem on the first midterm, so you have to study these problems. 오케이. 자, 여기 나오는 exercise 62페이지에 대한 연습 문제를 여러분들은 아마 꼭 풀어보세요. 요거는 이제 홈워크인데 제출을 안 하지만 여러분들이 이제 중간고사 볼 때 이제 제가 문제를 낼 수도 있으니까 이런 식으로 이제 오늘은 그래서 이번 주 오늘 우리가 끝마친 게 61페이지 이게 62페이지네. 62페이지까지 다 한 거고, 다음 시간에는 이제 우리 공부할 내용이 이제 코시 리만 이퀘이션 대해서 공부하겠습니다. 수고하셨어요.